All right, it's time for a little discussion of exothermic and endothermic reactions with some videos. These are things we didn't have time for in class, so I felt like it'd be worth making a recording of them for you. This first one will be the formation of sodium chloride from its elements, which means you're going to have to start with solid sodium and chlorine gas, which is the elemental forms of each of them, glass, to make sodium chloride. If you want to balance the equation, you can look at that for a minute. That should be solid sodium chloride. And realize that if you have 2 chlorine on the left, there better be 2 on the right, which means you better have also 2 sodiums on the left. Now, before we look at the video, let's now look at the type of reaction. Is this precipitation? Is this acid-base? Or is it redox? Well, precipitation, we're looking for 2 aqueous substances to combine and give you a solid product, which we don't have here. Acid-base, you have to have an acid and a base, which we don't have here. And this would therefore be redox, where elements are turning into a compound. The things on this question list are in the handout that was provided in class. So if you want to read along with this as I show the video, then you'll be able to help to fill in the answers. And so I will pull up the video next. Now for a video. Here goes.
Sodium metal is heated until it melts and just begins to burn. Then it is immersed into the yellow-green chlorine gas. The sodium begins to burn in chlorine with an intense yellow flame. It produces a white smoke of sodium chloride. We are observing the exothermic reaction of sodium metal with chlorine gas, producing the white solid sodium chloride. Afterwards, the glass spoon contains only white solid sodium chloride.
All right, that was a brief video. So let's go back to our screen and write in some answers. So the sodium has to be heated first to melt the sodium. And it also has to do with providing activation energy. Provides enough energy to make it go. The energy of activation is always needed to get a process started. If you were listening closely or watching closely, you should hopefully deduce whether this was endothermic or exothermic. I think they said it directly, that the process was exothermic. Heat is given off from this process, so heat is released. You had to heat it up a little bit, but more heat is given off in the general sense than is added if you total it up on the 2 sides, essentially. And that means that heat is a product. So those ideas should always go together. Exothermic reactions, heat is released, and heat is a product. The amount of energy is not specified here, but that can be determined from other sources. All right, let's look at another example. This is a reaction of copper to oxide. The video length is shown here. And let's determine what the balanced equation is going to be. We're going to take copper oxide, and it's going to react, that's a solid as it turns out, going to react with carbon, and we're going to make copper, whoops, pardon, this device is a little funny, copper as a solid, oh wow, and another product, turns out it's going to be carbon dioxide gas. I'm going to give it away to you, but I'll show you the video here in a second. Before we go any further, you should be able to deduce which type of reaction this is. I did not balance it yet. Oh, balance the reaction. What did I forget? Looks like we have enough copper on both sides of the reaction, but the oxygen's not balanced. So put a 2 on the left here and 2 on the right here, and that should be a balanced equation. So the category that fits the reaction should be precipitation, acid, base, or redox. There are 3 categories that we need to know about, and it's right there in the name. It's reduction because you're taking oxygen away from copper. It's being reduced to copper metal. The copper oxide is reduced to the metal. So in order to answer the rest of these questions, we should have to watch the video. So ready, set, go. Here will come your video.
In this experiment, we heat together a mixture of black carbon powder and black copper oxide. The gas evolved is passed into a solution of calcium hydroxide, that is lime water. Notice the white precipitate of calcium carbonate, formed as the evolved gas passes through the lime water. This shows that carbon dioxide is produced. As the black mixture is heated, the copper oxide is reduced to red copper by the carbon, which is itself being oxidized to carbon dioxide. After the tube has cooled, we can see the copper that has been formed at the bottom of the tube. When we tip out the mixture at the conclusion of the experiment, we can see that it is now red-brown due to the copper produced by the reduction of copper oxide.
Okay, so you can certainly replay that video if you please. So you can answer the questions. Hopefully you were thinking about the questions as it was playing. Why is the heat added? It's because you have to get the reaction started. And again, it provides the activation energy, start the reaction. And in this case, is the heat more produced or reactant? In this case, it's going to be constantly heated to keep the reaction going, and so heat is indeed a reactant. In that case, that tells us whether it's endo or exothermic. In this case, it is endothermic. And what is getting oxidized in this example? Well, what is gaining oxygen would be carbon, and what is getting reduced is the copper oxide. That means it's losing its oxygen, so it's reduced. Now, the funny piece that you might not understand with this right away, and you haven't probably necessarily run into this before, is that the calcium hydroxide is used at that lime water. They're bubbling the gas, the carbon dioxide gas, formed in the reaction through the lime water, because when you react calcium hydroxide with carbon dioxide, you make calcium carbonate. And that is one way of determining that the product, the gas that is being formed, is indeed carbon dioxide. When you react it with calcium hydroxide, calcium carbonate is formed, and other such things. We don't have to balance that whole equation, but it's just a means of detecting the carbon dioxide that has been formed. Okay, that was an example of an endothermic process. We don't always see examples like that. Let's view another reaction. This one's exciting. This one is called the thermite reaction. People like this one a lot because it's dramatic, and we'll have to see what the reactants and the products are. If you have your handout with you from class, the thermite reaction is actually on another page, and you don't have to come up with it completely. Let's watch a video and see which categories apply. Okay.
A metal crucible is filled with iron oxide and aluminum. A small amount of a white mixture of potassium chlorate and sugar is placed on top of the iron oxide aluminum mixture. A few drops of concentrated sulfuric acid are added to the chlorate sugar mixture to start the reaction. The reduction is extremely exothermic and proceeds with a shower of white sparks. The crucible becomes red hot. The aluminum has reduced the iron oxide to iron. When we look into the crucible, we see a ball of white-hot iron glowing at the bottom. When the crucible is cooled, we can remove the iron produced by the reduction of iron oxide and show that it is indeed iron by picking it up with a magnet.
So let's figure out the reaction that's being described here. It's iron 3 oxide, so it's Fe2O3, which is a solid, reacting with powdered aluminum, which is also a solid, to make iron as a liquid and aluminum oxide. Al2O3, aluminum oxide, is going to have that formula. It's also going to be a solid when it cools off. Now, when this reaction is balanced, what's lacking? I think we need some 2's. So put a 2 on the iron and 2 on aluminum, and that should be what it takes. At the beginning of the video, they show adding a mixture of white solid sugar and potassium chlorate, whose formula you don't have to understand, and some concentrated sulfuric acid. Why is that added? It's just to start the reaction. In other words, you often have to add something to get a reaction going. It provides activation energy. There is definitely heat evolved in the process of mixing those, the sulfuric acid and the sugar, and the potassium chlorate generates some oxygen. So the balanced equation is shown here, and I wrote it up there in the smaller space. Which category fits the reaction? So is it a precipitation reaction with two aqueous substances combining? Nope. Is it an acid and base? Nope. Definitely redox, oxidation reduction. You're taking oxygen away from iron, and so it is being reduced. And the aluminum is becoming oxidized by picking up the oxygen. So let's make that note. Gets oxidized and gets reduced. Those terms always apply to reactants. Is the heat a reactant or a product? So if you notice, there was no Bunsen burner or other flame involved, and so the heat that was shown was a shower of sparks once it began. I would say there was a lot of heat being given off, and so that would be what we describe as an exothermic reaction. Quite exothermic. Kind of a lot of fun. If you recall the smashing thermite with the rusted spheres and the aluminum foil on one of them, this is the exact same reaction but done on a different scale. All right, one more example now that involves catalysis, because we don't always understand catalysts. Catalysts are supposed to speed up reactions. So let's look at the example that's in your handout about catalysts. And, oh, sorry, back up here. Let me pause this for a minute. I wanted to talk about catalysis before that other chart. So we're going to look at a catalysis reaction where hydrogen sulfide gas is being formed from sulfur and such. So ready for another video. Here you go.
In this experiment, we are going to demonstrate an important industrial reaction, which is catalyzed by water. First, we invert a jar of colorless SO2 gas over a jar of colorless hydrogen sulfide gas. Then we remove the plate, separating them so that the two gases can mix. We note that on removing the plate, the H2S and sulfur dioxide do not react. No change is observed. Now, after a few minutes, we are going to add a few drops of water to the gas mixture. Water catalyzes the reaction between H2S and SO2, so that on inverting the jars to distribute the water, we begin to see the product of the reaction, solid sulfur coating the walls of the gas jars. And within 2 minutes, considerable solid yellow sulfur can be observed on the sides of the containers. This yellow sulfur is produced by the reaction of sulfur dioxide and hydrogen sulfide, a reaction which is slow unless catalyzed by a suitable catalyst, such as water.
An interesting reaction. The reaction then, we need to determine what was there. I hope you were taking notes as you viewed it. It was sulfur dioxide as a gas reacting with hydrogen sulfide gas. It's also known as rotten egg gas, something you wouldn't want to smell, which forms solid sulfur, which was the yellow substance, and water, which presumably was a liquid. You can kind of see there was a liquid in the chamber as it was mixed. Now, this isn't quite all balanced yet because not everything is coming out even. We have to come up with an even number of oxygens on two sides. So I'm going to put a 2 in front of the water, and that means we have to have twice as many hydrogens, so put more hydrogens here. And now we have 3 sulfurs on the left, so we should have 3 on the right. That should come out fine. Now, the catalyst is added, and we commonly write a catalyst over the arrow or under the arrow to suggest that it's being added but not necessarily part of the products. In fact, this one's an odd one because it does both. But it shows you how nothing happened until you did add the catalyst. It's much too slow. So what the catalyst does is speeds up the reaction enough to be noticeable in this case. What category fits the reaction is its precipitation. I don't see anything aqueous. Is it acid-base? I don't see, well, H2S might be an acid, but SO2 is certainly not a base, and H2S is a lousy acid, pretty wimpy as not noticeably. So it's redox. So what are we doing? We're turning a compound into an element, if you will. Or you could say you're reducing, this SO2 is getting reduced to sulfur. Taking the oxygen away from it is reduction. So the purposes of adding the water is speeds up the reaction It is the catalyst. It is a unique example because the catalyst shouldn't show up as a product, but it does in this particular case. All right, so examples of catalysis are not always obvious to you, and that's why I wanted to show that video. So one summary paragraph that might be helpful to you in looking at these endothermic and exothermic reactions in addition to catalysis was shown here for a moment while I passed it on and came back to it. So exothermic reactions, what? Heat is gained or lost from the system. It is lost. Where is the heat shown in the reaction equation? It is a product, and the value of delta H is always less than 0. In an endothermic reaction, the other side of this chart, heat is always gained. You have to add heat to make it go. Heat is therefore a reactant, and the delta H value is greater than 0. It may not have been obvious in these examples, but sometimes it was shown in our Pogel activity where the reaction of formation of water from hydrogen and oxygen. The sign of delta H for the reversible reaction is opposite. If one is positive, one is negative. So opposite that of the forward process. I hope these things help you understand exothermic and endothermic reactions with some nice little videos. Good luck with your studying. Ask lots more questions. Good luck with your homework. And see you in class.